So in this notes section, we're going to be taking a look at a number of different theorems about chords. So perhaps the first thing we should do is define what we mean when we say a chord of a circle. So a chord of a circle is any segment with endpoints on a circle. So for instance, a radius would not be considered a chord because it only has one endpoint on the circle. But a diameter, for instance, would be a chord because both of its endpoints are on a circle. But if you take any 2 points on a circle and you connect them with a segment, that's what we mean when we say a chord. So let's take a look at a few of the different theorems that deal with chords. And first we're going to look at this theorem, what we call Theorem 10-3. And it says, if two chords in a circle or in congruent circles are congruent, then something geometrically interesting happens. But first, I just want to take a look at this phrasing of congruent circles, and I just wanted to tell you what that means. Congruent circles are basically circles that are the same size. And if they're the same size, then that means they have equal radii or equal length for their radii. That's what it means if two circles are congruent. And we're going to see that phrase in a lot of the different theorems that we're going to be talking about. So I just wanted to kind of real quick get that out of the way. It means that I could be looking at two chords that are in the same circle, or I could be looking at two chords that are in different circles that are the same size. So if those chords are congruent, then let's think about what would happen. So if we look over here at this diagram, and if I told you that segment MN was congruent to segment PQ, both of those are chords, they both have endpoints that are on this circle T. If I told you that they were congruent, what geometrically interesting thing might you be able to conclude? Now, if I look at this picture and I see a couple triangles, I might recognize right away that those triangles are actually congruent by SSS. Again, given that I've told you that these chords are congruent. Because all four of these sides are radii of that circle, so they would all be congruent to each other. That would make these two triangles congruent by SSS. And now if those two triangles are congruent, you might notice then that would mean that this angle here and this angle here would be congruent. And what's interesting about that is that those angles are the central angles that correspond to these chords. If you look at those central angles, they contain, those angles are made by radii that go from the center out to each endpoint of these chords, right? This central angle has sides that are made of the radius segment TP and segment TQ, and P and Q are the endpoints of chord segment PQ. And then this central angle over here, its radii go out to N and to M, which are the endpoints of that chord. And so that's the conclusion to this theorem. If our chords are congruent, then our central angles will be congruent. So in this example here, angle NTM would be congruent to angle PTQ, or we would say over here, then their corresponding central angles are congruent. Now this particular theorem, like most of the theorems I'm going to talk about in this video, it has a converse to it that is also true. And if you remember, the converse to any theorem is where we just take the if and the then part and we kind of switch them around. So if you look at where I wrote it symbolically over here, it said if segment MN is congruent to segment PQ, then angle NTM is congruent to angle PTQ. Well, now what that would look like is we would be able to say that if angle NTM is congruent to angle PTQ, then segment MN is congruent to segment PQ. Or if I was going to write that in words over here, it would say something along the lines of if two central angles, and we would add in the part here that says in a circle or in congruent circles, if two central angles are congruent, then their corresponding chords will be congruent. their corresponding chords are congruent. And that's theorem 10-3. It's basically saying if the chords are congruent, then the angles, their corresponding central angles, will be congruent, and vice versa. If the angles are congruent, then the corresponding chords will be congruent. From that, we can actually kind of create theorem 10-4, which is going to look like this. If two arcs in a circle or in congruent circles are congruent, so if two arcs in a circle or in congruent circles are congruent. So now we're saying, okay, in this picture, let's suppose that arc PQ is congruent to arc MN. Then what would have to be true? Well, we can kind of reason our way through what would be true. Because if I look at arc PQ and I say that's congruent to that, and then I maybe real quickly draw in some radii, right? So let's draw in a radius out to P and one out to Q, and then one out to M and one out to N. Well, if those arcs are congruent, then these two angles have to be congruent, these central angles, because congruent arcs are made by congruent central angles. We learned that a couple sections ago. Well, and now we're in a situation like the converse of theorem 10-3 that says that if two central angles are congruent, then their corresponding chords would be congruent. So that tells me I would then be able to say that segment MN must be congruent to segment PQ, right? Or in writing, I could say if two arcs are congruent, then their corresponding chords are congruent. And then the converse would be true as well. So I could reverse what I wrote up here and I could say if two chords are congruent, right? Two chords in a circle or congruent circles are congruent, then their corresponding arcs are going to be congruent. Or over here we could say if segment MN was congruent to segment PQ, and if this is true, then we would know that, maybe I should write this in order. Maybe I should say arc MN would end up being congruent to arc PQ. And then from that, or kind of building off of kind of like the same idea, we can go look at theorem 10-5. And this one talks about two chords that are equidistant from the center of a circle or from congruent circles. Right? So I'm looking at these two chords here, segment AB and segment DC. Now, if S is the center of my circle, then the length of segment SF would represent the distance from this chord to the center. And I know that because segment SF is perpendicular to my chord, right? And we always measure, if we're measuring the distance from like a segment to a point, we have to measure along a path that's perpendicular to the segment. So SF represents the distance from segment DC or chord DC to the center of my circle. Segment SE is representing the distance from AB to the center. And if those two things are congruent or equal length, equidistant, right? If this and this are the same length, then what we know is that segment AB will be congruent to segment CD. And this has something to do with congruent triangles. I'm not going to, just for sake of time in this video, I'm not going to get into the proof of why this is true, but I will tell you it has to do with congruent triangles. Basically, we would add in some radii here and here and here and here, and then we would have some triangles that are congruent, and that would force these two chords to be congruent. But that's what we know, that if our chords are equidistant from the center, then they are congruent. And then the converse will also be true, which would say if two chords are congruent, then they are equidistant from the center. Or in this picture here, if I told you that segment AB was congruent to segment CD, you could tell me then that, say, segment SF and segment SE would be congruent as long as they are representing the distances from these chords to the center of the circle that they're in. Those would be congruent. Now we have a couple more theorems that I want to talk about real quick about chords. Theorem 10-6 talks about this situation where I have a diameter, segment CD is a diameter of my circle, and it is perpendicular to this chord AB. So segment CD is perpendicular to a chord, segment AB. You can see it's making that 90-degree angle. And there's two things that are going to happen because of this. And again, for sake of time, I'm not going to go through the proof, but I will tell you the proof has to do with congruent triangles again. But the two things that are going to happen is then that diameter, then the diameter, it bisects or cuts in half both the chord, right? It cuts segment AB into two equal pieces, but it also bisects the chord's arc. So because this diameter is perpendicular to this chord, we'd be able to say that segment AE and segment BE are congruent, but we would also be able to say that arc AC and arc BC are congruent because the chord for segment AB, or I'm sorry, the arc for that chord, the arc for segment AB would be this arc ACB. And so what's happening is this diameter is coming through and it's cutting that arc into two equal parts as well. And the converse for this one would say, kind of like what you might expect, it would say something along this line. If a diameter bisects a chord or the chord's arc, so if it bisects a chord or its arc, then it is perpendicular to the chord. So we could say if AE is congruent to BE, or if arc AC and arc BC are congruent, then we would know that that diameter, segment CD, must be perpendicular to the chord AB. And finally, this last theorem, we don't use this last one as much, but you might be able to kind of see it once I go through it. You'll see how it's true because theorem 10-6 is true, basically. And all it says is the perpendicular bisector of a chord will always contain the center of a circle, right? So if I drew this chord here and I had its perpendicular bisector, somewhere on that perpendicular bisector is going to be the center of the circle. Now what's interesting about that is I could actually find the center of any circle by drawing two chords and finding their perpendicular bisectors. Let me show you what I mean here just real quick. So I'm going to draw a circle, then let's draw a couple chords. We'll draw one in pink and one in light blue. Okay, so there's a couple chords. Now if I were to find the perpendicular bisectors of these, so like let's say I found out that the perpendicular bisector of the pink chord was this segment here, this orange segment, and then the perpendicular bisector of the blue one, let's say I'll draw this purple, so it might look about like that. So since if these are both perpendicular bisectors, meaning that if that's a 90-degree angle and that's a 90-degree angle and that's congruent to that, this is congruent to this. Okay, so this orange segment is a perpendicular bisector of the pink chord. That means that the center of the circle is somewhere on that orange segment. But then if this purple segment is the perpendicular bisector of this blue chord, then the center is also on that purple segment. Well, there's only one point that's on both of them. Their intersection point, right? That would have to be the center of that circle. So that's kind of a cool application for this last theorem here. Now there is an example problem that goes along with these. I'm going to let you try and work these out, and if you want to check your answers with me in class, you can. But I will say I think this is probably not one of the more difficult example problems that we've done. I bet you can figure out these 6 measurements in this picture here. Just take note that there is some information up in the instructions that's going to help you do that. Okay, so good luck.